Hi, I'm Mohamad Katanbaf from University of Washington. Today I present Relacks, Reliable Backscatter Communication in Indoor Environments. My co-authors in this work are Dr. Vivek Jain from Bosch and Professor Joshua F. Smith from University of Washington. We are surrounded by devices capable of wireless communication. For example, most appliances and many light bulbs are equipped with embedded radios that connect them to smart home networks. These radios can cooperate to form backscatter networks and deliver low-cost wireless connectivity to many everyday objects. This would enable many new applications, such as monitoring the temperature inside the pod or tracking human interactions with different objects in living spaces. While previous works have proved the possibility of biostatic backscatter communication with BLE, Wi-Fi, LoRa, or other wireless standards, the question of reliability of these links is not investigated thoroughly. In this work, we try to answer these questions: how reliable are backscatter links, and how can we improve their reliability? To better understand the reliability challenge of a backscatter system, I have simulated the received signal strengths for a BLE link and a backscatter link using free space path loss model. The number on each contour shows the received signal strength at the origin if the transmitter is placed on that contour. We can see that for a BLE transmitter with 0 dBm output power at 100 meters, the received signal strength is minus 80 dBm. A typical BLE receiver has a sensitivity better than minus 95 dBm, yet we know BLE as a short-range standard with practical ranges of 10 to 30 meters. This margin contributes to the reliability of BLE radios in non-line-of-sight applications and against multipath losses. We draw the same contours for a biostatic backscatter link with 20 dBm carrier power, where the carrier source and receiver are 10 meters away from each other. Even with 100 times more power, the received signal strength at most points is much closer to the receiver sensitivity level. We conclude that the backscatter links must operate on much narrower link budget margins. To investigate the question of biostatic backscatter reliability, we designed a BLE Backscatter Prototype. Here is the block diagram of the backscatter tag. We use an FPGA to implement BLE bitstream processing for the backscatter tag. We also add a low-power wake-up receiver to the tag. For transceivers, we use a commercial BLE chip and add a power amplifier to amplify the output for backscatter communication. Also, each transceiver supports 2 antennas. Please check the paper for implementation details. To better understand the effect of communication parameters on the backscatter link, we designed an experiment where the transceivers are placed on the opposite side of a 60 square meters room, and the tag is placed at 40 different points inside the room. At each point, we sweep the communication parameters including the frequency, transceiver's antenna, and the transceiver to wake up the tag and initiate the communication. We try each set of parameters 50 times. Each square on these heat maps shows the result for one parameter set. At each row, we see the effect of frequency diversity. If we look at points 5 or 10, we can clearly see that some frequencies have a superior performance. At point 4, we get good results from antenna pair 01, which highlights the benefit of antenna diversity at the transceivers units. At point 12, we get good results if we use transceiver 1 to wake up the tag. So we can expect high reliability if we select the communication parameters wisely. To this end, we must move from an open-loop system where transceivers follow predefined patterns to a closed-loop one. The closed-loop system filters high-loss channels and focuses on the good channels. Now the question is, how should we implement this? Besides the 3 devices, we use a controller in our system to collect the information for post-analysis. The controller initiates the operation. We use an active packet between transceivers to share the frequency, antenna, and wake source selection. Then we start the backscatter communication phase. Once all the results are collected, the controller selects the parameters for next round. We implement a scoring system to determine the best channels for communication, and follow this flowchart to ensure FCC compatibility and explore for other possible good channels. For more details on the implementation, please check the paper. We repeat the success rate test at the same 14 points using 3 different selection algorithms: random, propose algorithm with antenna diversity and without antenna diversity for both BLE coded and uncoded files. Our evaluation showed that following the proposed algorithm with antenna diversity, we achieve 81% average success rate over all points, which is 2.7 times improvement compared to the random selection. For more evaluations, including antenna orientation effect, environment variation effect, and long-time evaluation, as well as a sample application, please refer to the paper. So in summary, we design and implement a BLE biostatic backscatter system and use it to investigate the effect of frequency, antenna, and wake-up diversity on the reliability of backscatter links. We propose a closed-loop configuration selection algorithm and show that it significantly improves the backscatter system reliability. And finally, we evaluate our system in many different static and dynamic environments and show one potential application. Thank you.